thank Alexandra for this great invitation. So I'm an academic, so my slides will be academic slides, which means you're going to have a white background and then text will be in black. So I'm going to talk about artificial intelligence. I'm working at CentraleSupelec, affiliated with Inria. I'm thankful to ERC, who has been funding my research. And I have to figure out a way of moving. So I will start with two disclaimers. The first one is actually, I'm not an AI person per se. So my background is machine learning, computer vision, and biomedical image analysis. So I do not consider myself as an AI person. I think it's very important. The second disclaimer is actually that neural networks, which actually is a hype today, and they're used a lot, is artificial intelligence. But unfortunately, artificial intelligence cannot be summarized only on neural networks. There are many other methods that have been around for ages, and we shouldn't neglect them. OK, let's start with two historical statements. 1950, a very famous mathematician called Alan Turing predicted that 50 years from 1950, people, an average person, will not be able to separate or distinguish whether he's communicating, interacting with a computer or another human. OK? So around the same time, I think 7 years later, Alan Newell and Herbert Simon, who also got the Turing Award, predicted that 10 years from their statement, computers and artificial intelligence will be able to beat and become world chess champions. These are very well-known statements in artificial intelligence. And let's see where we stand. Well, I think Alan Turing's statement was an epic fail. If you take today the most advanced personal communication systems, like Alexa from Amazon, Siri from, I think it's Apple or whatever, makes no difference, and you try to put them to communicate together, you're going to have a lot of fun. I mean, putting two machines to discuss each other means there is absolutely no logic on the discussion. So I think we're far away. The second statement, I think, also was an epic fail, in the sense that it was predicted that it will happen in the 1960s, and it happened in 1997, when actually Deep Blue was able to win Garry Kasparov. So it took us 40 years between the time that people thought that artificial intelligence would be the revolution until actually we reached this stage. So the way usually we do artificial intelligence is through machine learning, and I think there was a lot of discussion before. So what we will do is something very simple in mathematics. Well, I'm going to somehow try to reproduce human intelligence. It can be a very fancy neural network. It can be another mathematical model that is doing some kind of classification. So this is going to be my model. And once I have defined my model, usually what I will do, I will try to actually instantiate this model from the data. So I'm going to use training examples, which usually come from humans. And then I will try to reproduce the behavior of the data through the model. And this is happening through training and optimization. So any artificial intelligence algorithm, which now is very popular, consists actually of programming a very straightforward mathematical logic that actually is trained from examples. That is the idea. If we look on the two examples that I mentioned before, because I think are very, very interesting, let's take the first case, which is actually the chess example. Well, the underlying principle of any game, or even if I go even to more advanced things like Jeopardy or Go, is that what you would like to do is, given the current state, being able to choose from a number of future finite states, which is the best one. So at given a system, which is deterministic, and what you would like to do is you would like to find what is the best possible action for your system, given the current state, and eventually what you would like to do. So the problem is very simple. What you have to do is you have to enumerate as many as possible hypotheses in the future. And if you are able to enumerate, the more hypotheses you do, then better the performance of your system will be, because you're going to be able to go even deeper and deeper on your simulation, okay? Because you have a finite number of states, okay? So when computing power is increasing, it's natural that all these systems will actually outperform humans, because humans are not that good on enumerating hypotheses in the future. So when you have a problem where you have a finite number of states, and your objective is to be able to predict the future, then machines will do certainly better. That's for sure, especially when you have more and more data. If we take the second example, which is the Turing test, it's something very, very different. Well, when you are discussing with someone, you have to be able to understand what he's saying. You have to be able to reason, which is a very different problem. So you have to be able to do natural language interpretation, which means parsing, not only understanding words, but understanding the meaning. And this requires parsing languages. So it's a very complex problem. Even if you are able to do that, then you should be able to do natural language generation, which is also a very complex problem. If I take a very simple example, and I use any of the personal assistants you can imagine, if you ask, for example, Alexa, who is the French president, most likely will answer Emmanuel Macron. If you ask Alexa, who was the former French president, he will ask Hollande. Most likely he will say François Hollande. If you ask them, who was president first, Hollande or Macron, most likely they will fail. So when you have to answer a specific question where the objective is clear, things are fairly simple. When you have to compare things, when you have to introduce reasoning, things become far more complex. So the idea is when you go to states where actually you have a finite number of hypotheses and your objective is to enumerate intelligently as much as you can, AI systems, they do a fantastic job. When you have to introduce cognition, things become far more complex. So the first thing is what we call some symbolic data-driven AI. And the idea is that you just replicate black boxes. You try to imitate the behavior of your data, which actually is going to give you the best possible strategy, and this strategy will be the collective intelligence coming from all of us. In the second case, what you have is what we call symbolic or rurally driven systems, because you have to introduce the notion of context. You have to introduce the notion of global understanding of the discussion. And these are two very different problems. So symbolic interpretation, and this is what was the origin of artificial intelligence, and this was the glory of artificial intelligence between 1950 and 1970, consists actually of parameterizing the space or solving your problem through an explicit formulation. You assume that you know what you want to do. You assume that you have rules which dictate how it should be the best possible action given the current state. Okay? So everything is written in your model. You are able to explain what you are doing, what is the decision you are taking, and why you are taking this decision. So, and there are plenty of systems like that. At the very beginning, you have expert systems, probabilistic interpretation. There were languages, programming languages, like Lisp or Prolog, for those of you who are a bit older, like myself. So these are things that actually, they do not explore only the power of data. What they are doing, they are introducing cognition into the decision process. That's the idea. Expert systems. The second class of methods is what we call data-driven methods, and this is what all machine learning methods they do, where the idea is very different. You don't try to understand what you are trying to solve. You don't actually even care. What you like to do is to be able to reproduce the behavior, the underlying behavior of the data. So you're going to try to build some kind of machine learning algorithm, which can be any algorithm you can imagine. And the objective of the algorithm is not to understand the problem which is trying to solve, but just to reproduce the behavior of your data. So you're going to have annotated data, and your objective will be to define a pipeline which you don't understand, which can be fairly complex, but is able to reproduce this behavior. And this is what we call machine learning. What we observe now is that machine learning has moved a lot, and the hype is what we call deep learning, which is a particular class of machine learning. And the idea of deep learning, and I think there's going to be a talk afterwards, which so I'm not going to spend a lot of time, is replicating very simple operators, which usually constitute of a very simple convolution actions or linear actions with many, many layers. So by putting this very complex model, which actually consists of very simple operations from one level to the next, you are able to get fantastic performance. And I think the next talk will be about deep learning, so I'm not going to talk about that. So let's now just try to look what is the status and what is the interest of this presentation. Well, some symbolic or data-driven methods, you don't need to be an expert. Actually, if you have enough data, you can use any of the existing libraries like Torch or any other library, and it will do the job. Okay? The second advantage is that for specific tasks, especially in vision recognition, which is my domain, we are seeing amazing performance, which we never imagined before. So there is a huge, at least an order of magnitude of improvement for all the tasks relative to visual recognition. And another thing which is very important is, since this is very simple operations, linear operators, once you have trained your model, then it can run on a very, very simple machine or a very low memory or low computational power terminal. So you don't need to have computing power. On the negative side, so we have to worry about training. So the more data you have, it takes forever. You need massive amount of annotations, and I think that's one of the most important limitations. If you don't have enough data, since these are highly complex systems, most likely they will fail. And most important, the two things that actually make these methods quite problematic for a number of fields. First of all, the solution is not human interpretable. You are getting a black box, and the black box is what you have. You have no clue why the black box is working. You have no clue when the black box is not working. You cannot predict failures. So that's very important. And two other things which are also limitations are overfitting. So since these are highly parameterized models, you're going to get most likely overfitting and training and generalization. If we look on symbolic methods like expert systems, this, because you are putting the intelligence on your model, you can train them with very few examples. Computational efficiency is there because these are fairly low complexity models. The solutions are fully interpretable. They respect the logic, and this is the logic of the designer. On the other hand, the main limitation is that you cannot build them if you are not an expert. You need to have you need to be an expert on the field in order to be able to design the right model. The performance, especially when compared with methods that are exploring massive data, is exponentially dropping, and there is no scalability, modularity, and portability. And that's the reason why they threaten distinction nowadays. Let's now conclude with two slides. The first slide is about open issues. The first thing I think we have to consider is what we call accountable AI. We have more and more solutions in the market, software that actually is predicting things, software is making decisions for us, and they don't necessarily adopt human reasoning. I mean, these are just adopting the behavior that was observable in the data. So how do we actually impose accountability? Who is responsible when you have an autonomous car and this self-driving car, and there's an accident, and you have the choice between actually throwing the car to a bus station or throwing the car to a tree, but you know that the damage in the bus station will be not that important. Who is accountable? Who takes the responsibility of the decisions taken by the algorithm? The second thing I think, which is going to be a major breakthrough, is what we call small data AI. And I think this is also applicable for things like deep learning. For a very simple reason, there is a lot of work in the academic literature where actually people were able to demonstrate that once you have trained your very complex model, you can compact it and throw out something like 95% of the volume of your network, and then you can still get this about the same performance, which means that you can have a 5% model guaranteeing the same performance, which from a mathematical viewpoint means that we are doing something wrong. There is no reason, if you can train a model and then you can throw out information and you can get the same performance, why you cannot train the smaller model from the very beginning. Because if you are able to do that, then you don't need that much data. Okay, so being able to do small data AI, I think, will be very important because there's going to be many of problems where you're never going to have enough data. You're never going to have enough applications. Another thing which I think will make a big difference is what we call integrated AI. I think now all recommendation systems, they do a fantastic job if they have a given objective. If they have a given answer and give a question to answer. So you train things to answer a question. And if it's just a single question, we are doing a fantastic job. However, if I take the example of oncology, well, what we're observing in images can be the outcome or the byproduct of many different diseases. You cannot only take decisions based on images. You have to be able to integrate information coming from other sources. So being able to introduce the notion of content, relative decisions, integrate AI, I think will make a big difference. And the last thing is about ethics. I mean, it's okay, we're building algorithms. Algorithms are supposed they have a reason, in many cases, to make money, because that's society. So if you keep retraining an algorithm with the decisions that the algorithm is making, most likely you're going to start to excluding people. And since these are black boxes methods, we don't have a way of controlling what is happening. We don't have a way of understanding what is the decision behind project. And the last slide about the future, which I think is applicable to researchers, startups, and founding agencies. So we have to be able to solve full-scale problems. I don't think success can be just the result of solving a specific problem. If you're not able to see the whole picture, even if you can do a fantastic job on a sub-problem, still you're missing the picture. So introducing the notion of full-scale problem, I think will make a big difference. We're not going to be able to solve problems if we don't have domain knowledge. I don't believe that any of us can become a radiologist by training 3,000 images in one day. And even if he can do that for a specific problem, when you're going to have a slightly different disease, he's going to miserably fail. So I don't think that actually you can have this generic knowledge which can be propagated from one application to the next. You have to be able to know what you're looking for, and then you have to be able to influence your algorithm such that this knowledge is propagated to your model. Okay? I think having data is very important. I mean, if you're not able to have access to the right data, you're never going to be able to train the right model. So this was mentioned before, garbage in, garbage out. And of course, I think having algorithmic supremacy, I mean, it's something very important. Now we have the impression, and that's an academic impression, that actually the world is full of AI experts. Okay? So I'm not that old. So I remember around 2010, the world was full of big data experts. And then they disappeared. Around 2013, 14, the world became again full of data scientist experts. Okay? And all these people, again, they disappear. And now we have all these AI persons that they reappear. So I think being able to manipulate a machine learning framework, whatever framework you can imagine, it helps a lot, but it doesn't make you an expert. You need to know the domain, you need to have the right algorithm, you need to have the right access to the data, and you need to have the whole picture. This is the only way you can succeed.
Thank you very much. Come have a seat with me. We'll take on a few questions. All right, great. Do you guys want to start with a few questions directly? Okay, because you get a question at the end of the room there. I just wanted to have one question for you. Now that you've done a lot of theoretical, how does the theory actually hit the ground? How does a lightning bolt hit the ground? Where does it hit? Are there some concrete examples that you see, other than the IBM example, that you see where artificial intelligence is really changing things?
I think for any given task where you have to answer a very simple question, then AI will make a big difference. For example, automatic translation systems, they do better than humans. Yeah. I mean, lip recognition, people actually that are talking, you're able to better understand what they are saying. A computer is able to understand what they're saying than a human. But you need to have a lot of data. So if you have to answer a very well-defined question, and you have enough data, and this is the case for radiology as well, it's normal and sure that humans will never be able to beat the computer, especially given the increasing accessibility of computing power, which allows you to go even farther, simulate more, learn more.
Okay. Yeah, question in the back there.
Yes, so you said that Turing's prediction was an epic fail. Are you saying that no system today meets the Turing test?
I don't think that many systems, maybe Watson is meeting the Turing test, but if you take an average system, it doesn't actually meet the Turing test. When I say it was an epic fail, it's because it was predicted that it will happen in 1990, and now we're 2017, and even if you take the most advanced personal assistant, I mean, for basic things, it works pretty well, but when you have to engage discussion about content, deeper discussion, things are not that great.
Okay, thanks. More yeah, there you go.
Hi, Nikos. Thank you for your presentation. That was very refreshing. And thank you also, Jean-Philippe. My question, which I would have asked to Jean-Philippe also, is when you didn't talk about ethics, but the first point, I don't remember what it was. It was like the...
Accountability.
Yeah. So, because we're seeing, like, for example, Tesla cars, they're getting into artificial intelligence. And I know that when it got to plane, like the autopilot in plane made a big revolution in, lowering the number of accidents in plane. I think it would be the same for cars. But either accountability or ethics, how do you think it's going to go tomorrow? For example, if you get one car, you are 4 people in the car, and somebody is making a mistake on the road, and the car just goes and decide that sacrificing you would possibly, make less sacrifice than, making 4 other cars that could potentially have 4 people in each car. Yeah. How do you think we're going to go? Is it like supervised learning?
Yeah, so I think our society is based on what we call rule-based system. So we have rules, and that's what defines ethics, okay? So if you're driving, then you know that if you're hitting someone, you're responsible. The problem with AI solutions nowadays is that these are methods that actually you don't control. You cannot predict failures, which is very important, and you don't know how they will react, because if they were not, most of these methods, they explore what was seen in the data in the past. So if you don't have enough data or you never observed this scenario, you have no clue how the system will work, which is not the case for humans. I mean, we have some logic. So I think this possibility, and this is not only for cars, I think at some point AI systems will make medical decisions, okay? And medical decisions might be correct or might be wrong. Who is responsible? Is the system? The company that developed the system? IBM is responsible that actually it failed to discover what was supposed to be discovered? It's the user that actually used the system? It's the hospital who bought it? So there are plenty of ethics and accountability issues which for the time being are ignored and are not even discussed. And it's not as straightforward, because the moment that I'm not an AI, I think AI is a great thing and that will change our lives. But you have to be able to control what is happening, and you have to be able to understand what is happening. And I have the impression that the direction we're heading now is just produce what the data is saying without caring about these questions, which are deep, and I think will have certainly a huge role in the future.
Nikos, thank you very much. And will you stay on for the cocktail after? Fantastic. Thank you so much, Nikos.